Introduction to Parallel Coordinates Plot. Cartesian Coordinates Plot Construction. Before we describe parallel coordinates, let's refresh our memories in terms of how to construct a Cartesian coordinates plot. The table on the left shows 4 different points with the 2 variables x and y. Each point is located on the Cartesian coordinates on the right. Point 1, 0, 0 is located on the origin. To identify point 2, 2, 3, we move 2 units to the right of the origin and 3 units upwards from the origin. Point 3, minus 3 and 1 is located 3 units to the left of the origin and 1 unit above the origin. Also, we can follow a similar process for identifying point 4. What happens when you try to plot more than 2 variables on a Cartesian coordinates plot? This is what the table looks like when we add 3 more variables called z, alpha and beta. The more dimensions we have, the more difficult it is to plot them on the Cartesian coordinates plot. When the point has more than 2 variables, we are not able to perceive and understand the point's variables on the Cartesian coordinate easily. The more variables you try to plot on the Cartesian coordinates, it quickly becomes infeasible. Is there any alternative to the Cartesian coordinates that lets us plot multivariate data? We can use parallel coordinates plot as an alternative way to address the challenge of high dimensionality. Parallel coordinates plot construction. This is the same table we looked at earlier. Each line on the parallel coordinates plot represents one point in the table. This parallel coordinates plot shows 2 data attributes, x and y, with 2 parallel axes. The origins of the x and y axes are at 0. To find the x value of the point, we start at the origin and move n numbers of units along the x-axis and plot the first point on the x-axis. Similarly, we move n number of units along the y-axis from the origin and plot the second point on the y-axis. Then, we connect these points with an edge. For example, to draw the edge on the parallel coordinates represents point 2, we move 2 units up from the origin on the x-axis, and we move 3 units up from the origin on the y-axis. Then we connect the point on the x-axis to another point on the y-axis with an edge. Correspondence between the Cartesian and parallel coordinates. Now, we are going to describe the correspondence between the Cartesian and parallel coordinates plot and how a point corresponds to an edge on the parallel coordinates. For example, the corresponding edge of the point at minus 3 and 1 is drawn as starting from minus 3 on the x-axis and ending at 1 on the y-axis in the parallel coordinates. We can follow the same corresponding edge construction process for the other points. This example is only 2-dimensional. Let's see what happens if we add more dimensions to the parallel coordinates plot. Parallel coordinates with 5 variables. This is the table from slide 3 that we already saw before. We could not plot this data on the Cartesian plot, but we can plot this in a parallel coordinates plot. Each point in this table has 5 variables. Each point variable is represented by an axis and each point is described by an edge on the parallel coordinates. In this example, we have 5 axes and 4 polylines. The edge crosses each axis to show the corresponding value of the point on a particular axis. For example, the green edge represents point 2, starts at 2 on the x-axis, goes to 3 on the y-axis, then 1 on the x-axis, 3 on the alpha-axis, and ends at minus 1 on the beta-axis. Parallel coordinates with an example dataset. Let's look at the car dataset as a new example. The car dataset represents a collection of cars. In order to characterize the important attributes of each car, we record them in a spreadsheet. This car dataset shows 7 attributes such as cylinders, displacement, power, weight, acceleration, mileage values, and production year of different car models. Each polyline on the parallel coordinates represents an individual car model. Starting with top left of the image, we can read from left to right. For example, the first 3 car models have 8 cylinders. And then, if we follow the top edge, we can see the first car has 400 displacement value. If we continue tracing this edge, the power value is 160, the weight value is 4000, and acceleration value is 14. Identifying the data attribute relationship. The data attribute relationship can be defined as direct and indirect relationships or no relationship. This image also shows a similar car dataset with 5 attributes. If one data attribute value increases and the neighboring axis value decreases, this is how we find an indirect relationship in the parallel coordinates. When we look at the axis of mpg miles per gallon and cylinders, in general, mpg increases, the number of cylinders decreases. Therefore, we define this as an indirect relationship. Let's look at edges between horsepower and weight axes. In general, while horsepower increases, weight also increases. It results in many nearly horizontal edges. This is called a direct relationship. If the edges between axes don't provide any pattern, we can say that there is no relationship. In this example, we cannot identify any relationship between mpg and weight attributes. However, the order of axes can be changed to identify a new relationship. Parallel coordinate challenges. To track edges and identifying relationships between variables can be challenging due to rendering a large number of polylines. This may result in overplotted and intersecting polylines. These challenges can be partially addressed by colors in polylines. We can trace the colors across each dimension to see some correspondence. Also, the order of axes and data distribution can make it difficult to visually connect polylines across axes.